Fructose, which is more commonly known as the fruit sugar, is a monosaccharide which, as I say, is very much commonly found inside of fruits. Now, fructose doesn't really cause the sort of blood glucose sugar spikes that you see from like chocolate bars, sugary sweets, etc. And that's simply because when you eat fruits and stuff, fruits contain a lot of fiber. Now, fiber is something that sort of staggers the absorption of fructose and sugar in general, really, to inside of the bloodstream, and so it will sort of stagger it. The sort of blood fructose level will not be that high whatsoever, and fructose can't even sort of contribute to blood glucose levels anyway, because fructose and glucose are entirely different molecules in the first place, and fructose still has to be metabolized by the liver and then go through glucogenesis and glycolysis pathways to end up becoming glucose. And that means that it takes a very, very long time for fructose to actually sort of end up becoming glucose and contributing to blood glucose levels and doing all of the good stuff that glucose can when it's in a regulated amount inside of the body. And I want to sort of go through that metabolic pathway, that metabolism inside of this video, and just go through all the sort of enzymatic reactions plus a few more little facts, etc., about fructose just in this video. But first, we probably have to talk about the differences between fructose and glucose and why they actually can't contribute to the same blood sugar level. Those have the exact same chemical structure of C6H12O6. They have slightly different sort of chemical things about them, such as certain bonding positions and stuff like that. Now, the bottoms of the molecules are pretty much exactly the same. They have a CH2OH tail, plus they have the exact same OH groups, hydroxyl groups, on the sort of side of the carbon chain, but it's the positioning of the double bond that is the main difference between these two molecules, especially if you were looking at their linear structure. Fructose's oxygen double bond occurs one layer lower than glucose's double bond does, and this means that when this double bond opens up and ends up going around and attaching to where the lowest hydroxyl group would be on both of these, and then that same hydrogen that it replaced ends up getting added back on to where the double bond came off of. When it's in their ring structure, this means that glucose ends up looking like a hexagon. You may have seen in your school textbooks glucose look a bit similar to a hexagon, and this means that fructose in like your school textbooks, etc., seems to look more like a pentagon, and that is basically all of the differences between fructose and glucose. It should be a lot easier to understand when I put up the images on screen and sort of circle everything and make it a little bit easier to understand. But all you need to know is that they are different, they are isomers, and this means that they can't contribute to the same actual blood sugar level because they aren't the exact same type of sugar. Now, what's interesting is that glucose and fructose in the environment have actually been combined to make sucrose, and sucrose is commonly known as table sugar, and this can be extracted from so many different things like sugarcane, etc. But the problem is that this isn't metabolized by the liver. This is simply metabolized by a single enzymatic reaction inside of the gut, which will split both of the molecules apart. It will create a glucose molecule and a fructose molecule. The glucose molecule will contribute to a blood sugar spike, but the fructose molecule will then have to go through all the enzymatic steps that we'll talk about in this video to actually end up becoming glucose. And there's so much to talk about in this video that, yeah, I may not be able to cover it. I may have to cover it in a few separate videos because there's a lot of different whole section things. It's very confusing, but I hope I can kind of make it as easy for you to understand as humanly possible. But the first step, the first reaction inside of the metabolic pathway from fructose all the way to glucose is fructose turning into fructo-1-phosphate using the enzyme fructokinase. Now, fructokinase is an enzyme, and you may notice the sort of suffix kinase on the end of this. Now, kinase is like a specific type of enzyme which adds a phosphate group onto the molecule that it's sort of catalyzing, and you will know that fructo-1-phosphate essentially is just fructose with an added phosphate group on it. And I don't know why a lot of reactions sort of have to have phosphate groups added on it. It's just because that's just how the body works in its wonderful, fragile ecosystem, and it end up becoming glucose after a couple of reaction steps, which I'm going to go through in the future. But some people can actually be deficient in the enzyme fructokinase, and this means that their cells, their glands, do not have the ability to produce fructokinase because either its production is inhibited or they simply do not have the genes nor the DNA to actually produce this specific enzyme. And if that is the case, then it doesn't really have too much of an effect, because hexokinase is another enzyme that will simply catalyze fructose into fructose 6-phosphate. And I will mention fructose 6-phosphate towards the end of this video because it has a few little special impacts, but just keep that in the back of your mind that if you are deficient in fructokinase, then hexokinase will produce fructose 6-phosphate, and I'll explain why that is needed towards the end of this video. Now, the second reaction step inside of the metabolic pathway from fructose to glucose is fructo-1-phosphate, as we talked about earlier, turning into two separate molecules known as glyceraldehyde and DHAP. And this reaction is catalyzed by the enzyme aldolase B. Now glyceraldehyde and DHAP, I can't actually remember what DHAP stands for. I'll probably put it up sort of as a text box on the screen or whatever. Now, while glyceraldehyde and DHAP are completely different molecules, they can turn into the same molecule just using different enzymatic reactions. And that same molecule is G3P, glyceraldehyde 3-phosphate. And glyceraldehyde turns into glyceraldehyde 3-phosphate using an enzyme known as triokinase. And DHAP, which stands for dihydroxyacetone phosphate, ends up turning into G3P using an enzyme which I can't quite remember the name of, nor do I have a specific abbreviation. I'm pretty sure it's like some sort of trio kind of thing, just like triokinase was, and then it's like triophosphorylase and something like that. I'll put the thing up on the screen so you can understand what it is, but for now I've completely forgotten it. But G3P is interesting because G3P enters the glucogenesis and glycolysis pathways. Now, the glucogenesis and glycolysis pathways, I'm going to go through in a separate video, but what's interesting about the glucogenesis and glycolysis pathways is this is essentially the breakdown and the production of glucose. Now, G3P, to produce glucose, will have to go through a few more reaction steps, which I'll go through in the glucogenesis and glycolysis video, to end up becoming glucose. But there's like a whole load of reactions that need this to happen. But what's very interesting is that from fructose, which is very, very similar to glucose when you consider its chemical formula, and its structure really isn't that different either, that it takes so many reaction steps just to actually change it from fructose to glucose. I personally find that very interesting. You'll find that a lot in sort of science, where very, very similar molecules will need so many reactions just to actually become the molecule that it needs to be to act on the body. I mean, cholesterol and lanosterol is a very good example of this. I've done a video on that if you want to check it out. But lanosterol looks very, very similar to cholesterol, yet it takes 18 reaction steps for lanosterol to turn into cholesterol inside of pretty much every single cell inside of your body. And to me, that's a very, very interesting thing. That's why I like science so much. But if we go back to sort of the whole metabolism of fructose, one thing I did want to mention is that fructose can actually be bad for the liver if it is metabolized to an excessive amount. You may know that in some sort of sugary drinks, Haribos, the sort of fruity kind of sweets, a lot of this stuff uses fructose syrup to actually make its sweet and taste nice and sort of taste a little bit like fruit. The problem is that fructose can cause things like fatty liver, black liver, and when your liver has to excessively metabolize fructose, it just doesn't end up reacting very well whatsoever to the excessive amounts of glucose, and it won't go through the sort of normal metabolic pathway, and it will simply end up just being immediately turned into fat by a whole other process which I may cover in a separate video. But this will end up turning to visceral fat. It will just sort of coat the lining of your liver cells, and that's just not good news because it will sort of constrict your blood supply, just do a whole load of bad things to your body. Visceral fat is essentially sort of body fat that you can't actually see. It's fat that's under your muscles, and sugar, fructose, and sort of things like alcohol all cause visceral fat to develop on the sort of outside layer of your organs but below your muscles. Visceral fat is just not good news for anyone who has it because it can be a leading cause of metabolic syndrome, things like cardiovascular disease, obesity, diabetes, and all that just awful, nasty stuff. hang on a minute. Do you remember when I mentioned fructose 6-phosphate right at the start of the video? Now, fructose 6-phosphate also enters the glycolysis and glucogenesis pathway just like G3P does. So even if you are deficient in an enzyme like fructokinase, it doesn't really matter because you have hexokinase to end up metabolizing from fructose into fructose 6-phosphate, which then ends up in the same pathway that G3P does. Now, I'm pretty sure I've covered absolutely everything that I wanted to in this video, and so with that, I hope you enjoyed. I appreciate it very much that you stayed to the end, and I also recommend subscribing because I love this community of young tribal people who are willing to improve themselves so much more than they already have, and good luck.